No, not soon, right now.
Well, I mean, right now. That's what I mean by soon.
Very good. So we want to start at exactly 20. So in this 1 minute, let me just say a few words. Well, first, let me thank Jaume and Zohar for beautifully giving the example and sticking to the suggested time perfectly. And let me remind you that the idea of this discussion, Nati and Xiao-Gang will give us 20-minute introduction to prime us. And thankfully, they already sent us the PDF. So for the non-experts, do check out, I hope you checked out the PDF beforehand to motivate yourself to think of questions. Speaking of which,
Are we connected?
Pedro seems to have been disconnected.
Am I connected?
Yep.
Yeah, we hear you.
Nothing. So I can take over until Pedro comes back. So I guess he was going to say you now have 20 minutes. So Nati, are you going to go first?
Yeah, I'm going first. Can you see my screen and pointer?
Yep.
And can you hear me? I assume you do. So first, I'd like to thank the organizers for this fantastic conference, which was subject to almost impossible boundary conditions. So I really congratulate them for this heroic achievement. And this is the first presentation Xiao-Gang is going to follow. And since we're going to have some kind of a bird's eye view of where we are and where we are heading, and I have only 10 minutes, I decided not to have references on the slides. We've had enough references elsewhere. Otherwise, it will clutter the slides and the presentation. So the first question I would like to address is, why should string theorists care about this topic, the topic of phases of matter? And in fact, over the years, I've heard many senior people, very famous physicists, making comments like the following: condensed matter physics is not fundamental physics. String theory is fundamental physics, but condensed matter physics is not, and therefore I'm not interested in condensed matter physics. Another comment I've heard many times is that quantum field theory is already fully understood. There's nothing new to be discovered in quantum field theory. Quantum gravity is the real frontier, and there's no reason to pay attention to quantum field theory. Well, the first comment I would like to make is that I strongly disagree with these two views. Looking historically over the last several decades, we have seen deep and productive cross-fertilization between condensed matter physics and high energy physics and string theory. I think it's fair to say that almost every idea in high energy physics or string theory either had its roots in condensed matter physics or had implications in condensed matter physics. And I prepared slides, which I'm not going to show, with a long list of examples. Based on this past track record, I expect developments in condensed matter physics to inspire more developments in high energy physics. And for this reason alone, I think string theorists should be interested in the subject. In addition, and this is in addition to the intrinsic interest in the subject. Since this is a discussion session, I could focus on many different aspects of the topic, and I decided to focus on a particular aspect, and Xiao-Gang is going to focus on another aspect. And the aspect I'll focus on is something that has appeared in many of the discussions and presentations in this conference, including beautiful presentation by Jaume earlier today. And this is the question of separation of scales. It appears in all of science, including physics. In philosophy, it's known as reductionism. In quantum field theory, it is known as the renormalization group. And this is the statement that physics of phenomena at one length scale are almost independent of phenomena at shorter distances or at longer distances. This didn't have to be so simple, but it is a fact that this is true. And ultimately, this fact stems from the fact that physics is local. Locality means that what happens at different scales is almost independent. More technically, we start at short distances based on theory in the UV. It can be on a lattice or in the continuum. And then we describe what happens at long distances in the IR using an effective universal description. And it's effective because it is independent of most of the details of the short distance theory. And that another reason it's effective is that it's very useful. And this picture has been very useful in two directions. First, quantum field theory that appears here in the IR allows us to classify and organize all possible phases and also the transitions between them. So this is an application towards condensed matter physics, but also in the opposite direction. New physics, new phases teach us something about quantum field theory. So this has been a dominant paradigm in physics in general and in quantum field theory in particular over the last several decades. However, there are some notable counterexamples which I think should be highlighted. I think that we can call them all UV-IR mixing. This is what characterizes them is that separation of scale breaks down. And there are some long distance, low energy phenomena that reflect high energy physics. We've seen some of that already in this conference, reflecting the fact that this is common in gravity. In gravity, if you try to localize a lot of energy in small volume in order to probe what happens at short distances, instead of probing the short distance theory, you create a large black hole that hides the short distance physics. So this is well known and it appeared in some of the discussion sessions. Also, dualities in string theory relate small distance and large distance. T-duality is the prime example of that. And also many questions and confusions in quantum gravity circle around this issue and the issue of locality, and I can point to the information discussions and to other discussion sessions here. Now, somebody could say that in the context of quantum gravity, space-time will ultimately be emergent. And if space-time is emergent, the notion of distance is emergent. And therefore, we shouldn't be surprised that long distances and short distances are mixed together because the whole notion of distance is going to be an emergent approximate concept. How about theories which do not involve gravity? Well, we have some examples which provide counterexamples to the separation of scale paradigm, also come under the name of UV-IR mixing, and they arise as follows. First, we can start with string theory and turn off Newton's constant. If we turn off Newton's constant, we have a non-gravitational theory. That has been a very productive and useful machine to produce quantum field theories, and we heard about them in many talks in this conference, including the talk earlier today about the 2-0 theory and its compactification. All these theories are standard quantum field theory, but in certain peculiar examples, what this machine produces is not a standard quantum field theory because it exhibits UV-IR mixing. Let me mention two prominent examples. The first is a little string theory, and it's characterized by having no local operators and T-duality. These two facts reflect the UV-IR mixing. T-duality means short distance and long distances are the same, and no local operators prevent us from exploring things at the point. Another example is the example of an ordinary field theory, but not on a commutative, but on a non-commutative space. One way to think about it is to say that the degrees of freedom of the theory are dipoles. And if we give the dipole high momentum in the x direction, it actually grows in the y direction. And therefore, the interactions do not lead to separation of scales. The UV-IR mixing is prominent here because as we try to make high momentum in one direction, the space grows in the orthogonal direction. The same phenomenon appears also by computing loop diagrams. And when we compare the theory on the commutative space to the theory on the non-commutative space, the theory on the non-commutative space has fewer UV divergences. And these UV divergences that we lose manifest themselves as new infrared divergences, again reflecting UV-IR mixing. In fact, I think that the phrase UV-IR mixing first appeared in this context. Another example appeared more recently, not out of string theory, but examples from lattice models. And I like to call them exotic lattice models, exotic because they have this UV-IR mixing, sorry. They include model of fractals, but also some models without fractals. And the characteristic fact about all these models is the subsystem symmetry, which eventually leads to the UV-IR mixing. This was summarized beautifully by Xiao-Gang this morning, so I'll be here extremely brief. The main point of a system with subsystem symmetry is that different submanifolds of space have different group elements. So we have a huge symmetry group where the group element is labeled by a position in space. For example, we can act on the XY plane at different values of Z, and different values of Z correspond to different group elements. So we have a huge global symmetry group. Since this is a global symmetry, operators and states must be in a representation of this subsystem symmetry. And if we have a huge group, the representations could be huge also. And as a result, there could be a very large ground state degeneracy. Ground state degeneracy that depends on the number of lattice points. This is very unusual in continuum field theory. In fact, it's almost impossible in continuum field theory where the number of ground states is finite. Also, the observables of the system are constrained by this enormous symmetry group. And if we have operators that are charged under the symmetry and we balance the charges and we have a non-zero correlation function, we can move one of the operators a little bit. And as we move the operator in space a little bit, the correlation function does not balance the charges. And as a result, the correlation function is zero. So correlation functions are going to vary on the lattice scale, even in the continuum limit. All these really manifest the UVIR mixing. If we try to incorporate that in a continuum quantum field theory description in order to describe the long distance behavior, we must use discontinuous fields, which is really opening a Pandora box. I'm not going to discuss it here. So let me end this presentation with a list of questions and challenges that I hope will provoke interesting discussion here. The first question is, what is quantum field theory? We know many formulations of the theory. We can start with continuum Lagrangians and perform perturbation theory or non-perturbative calculations. We can use lattice, bootstrap, integrable theories, have some solutions. There are some string constructions, etc. None of these formulations is perfect. Every one of them has its issues. But the main point is that none of these formulations really cover all cases. Sometimes we have the lattice, sometimes we have a string construction, sometimes we have a lattice and so forth. I feel it's important to look for other formulations. Other formulations will give us both deeper understanding about what's going on here, will also lead to new theories, as new theories are constantly being discovered, and more pragmatically, they will lead to new methods to perform calculations. Another aspect of it is that we should look for generalizations of quantum field theory. I highlighted here UVIR mixing, and I gave some examples. But for all I know, there could be other interesting theories, non-gravitational theories, that go beyond the standard framework of quantum field theory and will force us to generalize it. So I think I'll stop here and let Xiao-Gang continue. Thank you.
Thanks, Naj. So Xiao-Gang.
Okay, just as Nadia said, I'm going to give another example of a very close relation between string theory and the condensed matter theory. And the relation is so close, so actually I can give my presentation using a slide from a string theory. So here I'd like to thank Aaron for her excellent talk and slides. And so this basically some kind of like a strong planned program in condensed matter physics. So a big question in condensed matter is that which effective field theory describe a condensed matter system? Can we classify them? More formally, we can ask what kind of effective field theory have a UV completion in so-called local qubits model? Yeah. For the time being, we'll say without symmetry. So in this presentation, we just ignore symmetry. Also, we ignore the fermion. So the qubits really means a bosonic model. Okay, and certainly not every effective field theory can be UV completed as a local qubits model. Okay, so there may be anomaly cancellation, and maybe there's other additional constraints. So that is the issue. And in string theory or in quantum gravity, we like to have effective field theory, which is weakly coupled to Einstein gravity. And but in condensed matter, this condition is more relaxed. So anything with emergent gate theory also be very interesting, or emergent fermion, even though we start with a bosonic model, and even an emergent complete standard model. So that's connect this qubits model to particle physics. or can we have emergent graviton? So all those, when you have those properties, so that this effective field theory became more interesting. Okay. For the emergence of graviton right now is probably still kind of open. We all have example with emergence of a Lifshitz gravity, which is linearized Lifshitz gravity, but not Einstein gravity with linear dispersion relation. And when you have this, so with those emergence interesting field theory, so in condensed matter, it was called a new phase of matter. Okay. And if this interesting field theory have an energy gap, then we call them have a topological order. So actually, this name of topological order is motivated by Witten's Jones polynomial paper, and this which is it's a paper which gave rise to the topological quantum field theory. So that's really the motivation to name topological order. So in this Swampland program in condensed matter, so there's similar thing like a landscape, which is a consistent, a field theory which is consistent with the lattice qubit model, local qubit model, and there's a swampland which is more is inconsistent. So there's something wrong. So the key words here that those, even though for the field theory in the swampland they are apparently consistent, but somehow it's inconsistent. So what that really means. So in condensed matter, there's a way to give this apparent consistent, a more concrete definition. That is apparent consistent effective field theory can be viewed as a boundary of a local qubits model in one higher dimension. If these local qubits model are in a trivial phase, and then this effective field theory on the boundary will be in the landscape. Means this effective field theory actually have a UV completion in a lattice model in the same dimension. However, if this lattice qubits model or local qubits model are in a non-trivial phase, topological ordered phase, and then the boundary will have abstraction to have a qubits realization in the same dimension. So this is so therefore this question of swampland and the landscape can be answered very directly using this one higher dimension of this holographic point of view. Okay, so this is very much sounds like an anomaly, So this holograph point of view basically says that this bulk topology order in the bulk of quantum liquid is an abstraction for effective field theory to have a local qubits model UV completion in the same dimension. Okay, but this really sounds like an anomaly. And but somehow want to say that this anomaly actually is more probably called as a generalized anomaly. That is this swampness correspond to so-called generalized anomaly, which actually correspond to a bulk topology order. And so within this holograph picture, the usual anomaly is correspond to bulk invertible bulk topology order, which can be cancelled. So there's an anomaly cancellation. So all the this invertible gravitation anomaly, I think, is kind of more narrow sense, more usual anomaly we'll talk about. But however, from holographic point of view, most topology order in one higher dimension are not invertible. So their boundary probably can be viewed as a generalized anomaly. So this really led to a very strong interest in gravitational anomaly in condensed matter theory. Although in condensed matter people don't discuss gravity, but gravitational anomaly is a very good concept to understand which effective field theory can come from lattice model or qubits model, which effective theory cannot. And also we like to have this anomaly-free condition. So what are the anomaly-free conditions for this generalized anomaly? Again, we see a very strong connection to study in string theory. And one of anomaly-free condition in string theory in Swampland is a completeness hypothesis, but in condensed matter is called remote detectability principle. So that means every excitation can be remotely detected by other excitation by braiding remotely or some other operation remotely, which two excitations do not touch. So in order for effective field theory to be realizable by qubits model, their excitation should have this kind of remote detectability principle. Okay, and then another is a relation is again in string theory. There's a cobordism conjecture, and so that's if you translate that into the into condensed matter, they really say that all the effective field theory coming from a lattice model can connect to trivial phase by domain wall. Means it can have a boundary to the trivial phase, to the vacuum. Okay. And also, if two effective field theory cannot be connected by domain wall, that means they have a generalized anomaly, and their generalized anomaly are different. So their different generalized anomaly means they cannot be connected. And so that's really from holograph point of view. That means because you have non-trivial bulk, the boundary would extend into the bulk. So that's why the boundary they cannot be connected to each other. So all these are really related. And similarly, there's a notion that there's no global symmetry in quantum gravity. And but in condensed matter, this became a little bit of a trivial statement. That means no global symmetry in qubit system without any symmetry, because we try to replace quantum gravity by qubit system without any symmetry. But however, this statement actually is a little non-trivial because the low-energy effective theory of a qubit system may have an emergent global symmetry. But this emergent global symmetry should be all behave like a gauge symmetry. Or actually, it's not really there. It's just approximation. And then because of the topologization can have all kind of dimension, point-like, string-like, and etc. So therefore, this emergent symmetry can be very general. And as Xiao-Gang talked about in his talk. And the most general version at the moment, we see that is described so-called algebraic higher symmetry, or it's a mathematic foundation. It's a fusion higher category theory with a fiber functor. And this something replace group or higher group. So there's so this connection to the mathematics also very important. So here's my summary. This is just my last slide. So just summarize this very close connection. Thank you.
Thank you very much. So people can, of course, raise their hand to ask questions. But there was a question in chat, which just a naive question that I also have by Charles Wang. So the question is, if you just find some condensed matter state in the wild, so in the real world, would you expect it to be described by a local qubit model, or would it have to be?
The answer is yes and no. Okay, in condensed matter, the most system we're interested in is an electron system. So it have a fermion with a U1 symmetry and maybe with a gauge interaction. But however, if if you only study interest in the quantum magnets, we call this quantum spin model. The quantum spin model really is a qubit model. So actually, so in my presentation, I mainly talk about the possible effective field theory from a quantum spin model or from these quantum magnets. Okay, but for the metal and the conductor, one should generalize this a little bit to consider a fermionic model, a local fermionic model. So that's another thing. Yeah.
Thank you. So Xiao-Gang, you had the question or comment?
Yeah, Xiao-Gang, thanks for the nice presentation. So you discussed this notion of local qubit model without symmetry. I'm just curious, if I take a single qubit, so two state, and with a trivial Hamiltonian, is that in your swampland or it's not?
No, it's the single qubit is already a qubit model, so it's in a landscape.
But
and so the swampland really is referred to some kind of effective field theory, which is whose definition is not so complete, and in some sense, okay. And then we ask whether this effective field theory can be realized by some local qubits model as a low energy effective theory or not.
But a single qubit has a 't-Hoof anomaly. Right? A single qubit has a SU2 global symmetry, but realized projectively as SO3.
Yeah. So that would be okay. Yeah, that's a very good question. So that would be another issue. So here I'm talking about the local qubits model without any symmetry. Okay, and then there's the previous question is about the maybe you should consider local model with the fermions. Fermions have this Z2 fermion parity symmetry. And then the classification of a swampland as landscape is very different. Now you're asking, if you have a qubits model with some symmetry, then its corresponding swampland landscape also became different. And that's really very interesting question, because most condensed matter systems do have a symmetry. The qubit model do have a symmetry.
Right.
So then the definition of swampland and the landscape shift again. So this really, this really corresponds to study of anomaly, gravitation anomaly, 't-Hoof anomaly. But here I want to emphasize that all those anomaly study have the more general point of view using swampland landscape picture, using holographic picture, and that's maybe is a more general way to view all those anomalies. Yeah, that's my point. Yes.
Okay, thank you.
Zohar?
Hey, thanks. I actually have a short question to both speakers. So for Xiao-Gang, isn't the generalized anomaly exactly what I talked about? Isn't this the higher central charges? This is the situation where there is a non-trivial topological theory in the bulk.
Yes.
And the edge modes are protected by higher central charges.
Exactly. And so if I rephrase your results in this holographic picture, it means that the anomaly is about topological order
with
there are several to say that who is this topological order is a commuting projector model. Okay, that's one way to realize. Another way, mathematical way to realize that this topological order is a Drinfeld center.
That's right.
Yeah. And
but the Drinfeld center criterion is extremely difficult to check algebraically. So the point is that you can just measure the phases on length space partition functions, and
so that's why I think this length space indicator is really impressive. Yeah, I'm really glad to learn this.
Well, thank you. Can I also ask a very short question to Nari, or should I wait?
No, go ahead.
Yeah, go ahead.
So just as a general thing in EFT, and in effective field theory, the way I understand it is that it's an expansion in some separation of scales, right? I mean, it captures it gives you some asymptotic series in some ratio of 2 scales. And maybe sometimes you can get non-perturbative effects from effective field theory, but that's usually difficult. Now, if there's UV-IR mixing, what is the point of effective field theory? What is it generating for you? Which expansion?
So I don't know a general answer, but I know I can answer it in specific context. So in the little string theory is well-defined and they are observables. And it is separated from the underlying string theory. This is the expansion, and there's a well-defined theory, and people computed some observables in this theory. The problem is not with that. The problem is that the theory as it stands does not have UV-IR mix. It does not have UV-IR separation if you look at it at short distances. The same is true for the theory on the non-commutative space. There's a well-defined theory. There's a perturbative expansion. Say if you look at say 5 to the 4th, and people even prove renormalizability. So the same thing works, and you can compute various things. The surprise is that some UV divergences become unexpected infrared divergences. But there's nothing wrong with the theory, just that it does not fit your general framework. The theory describes everything, both the UV and the IR, and we don't have this separation if you try to take the answer and slice it apart. And the same is true with these exotic models, that there are correlation functions that can be computed using the theory, and they exhibit peculiar features. Let me give you an example. There are correlation functions between operators at separated points. Everything looks nice. And then, say, in infinite volume, but at special non-coincident points, there are divergences. So two operators at different points, and you move the points, they suddenly a divergence. A divergence that can be regularized by putting the system in finite volume. This is a typical UVIR mixing. There's a singularity when one point goes to a specific point, even though there's no operator there, and it's cut off by the size of the box. The size of the box is infinite, the answer is infinite. And on a case-by-case basis, I can give examples. I do not know a general framework. I do know that this does not fit the standard picture of the Wilsonian renormalization rule. And I really wish I understood it better. That's why I think I picked this topic for a discussion session. I did not report a result of a topic I understand, but I bring it more as a question to point for future research.
Thanks. Kumar?
Yeah, thanks for the talks, both Nathy and Xiao-Gang. I have a question for Xiao-Gang. So your parallel that you're drawing between local qubit models and the quantum gravity and swampland issues, is that just a parallel, or you really view local qubit models is a way to think about quantum gravity? What is your take on that? Is it just analogy or more?
Yeah, at the beginning, I thought it's just analogy. And because it's a two parallel theory, two different theories, there's a similar analog. But then after hearing the talk in this conference, and then this parallel is so amazing because of this swampland landscape point of view for quantum gravity, and the similar this local qubits model, it's such a strong parallel. So I cannot help to think maybe these two are the same. So I don't want to really say that, but I really want to entertain this idea. Maybe the two are the same. So basically, or maybe I'll put another way. So because the condition for swampland and landscape, whether there is a difference from quantum gravity point of view and from this condensed matter point of view, can we find some condition which they are really different? So then that really means the two theories are really different. But I don't really understand a swampland from string point of view very much. But from a little bit, I understand the similarity is striking. So that's part I want to emphasize. But it would be really interesting to see whether there's some anomaly-free condition which are really different from effective field theory from quantum gravity or effective field theory from qubits model, whether they enjoy really different anomaly-free condition. That's the question, yeah.
One question I have in that analogy is that in the swampland, we expect that the theories that you get in the EFTs that you get for quantum gravity are a measure zero compared to all the allowed ones. Is that the same for the local qubit models or not?
You mean landscape as a measure zero from this swampland?
Yes.
And yeah, I would say sometimes it's hard to define what to measure, but in general, yes. And the boundary for, okay, swampland belongs to boundary for topological order in one higher dimension, and the possibility of topological order in one higher dimension is infinity. So therefore, the landscape is a boundary for trivial topological order. So that's a one from infinity. So in that sense, it's a measure zero.
Nice. Okay. Thank you.
Irene?
Yes. Yeah, so first, thank you so much, Xiao-Gang. I really loved the analogy and the slides. It was very fun. And I found it super interesting. I mean, I think indeed there are many analogies. And also from Nathy, like the UVIR mixing, I think this is another topic which we deal a lot with in the swampland program, because we precisely try to understand this quantum gravity imprint at low energy. So it's precisely try to understand this, whether there is a UVIR mixing imposed by quantum gravity that goes against the Wilsonian effective field theory approach. And I had a question for you, Xiao-Gang, more concrete about one of the things you said. I didn't understand very well the analogy with the completeness hypothesis, like that seems that it has to be complete, otherwise you have some anomaly. I was wondering if you can elaborate a bit on that.
So actually, one example for this is the following. Let's consider a purely Feynmanic model. Or maybe let's consider this a standard model. In a standard model, we have a neutral fermion that do not couple to any gauge theory and gauge field. So that means that this neutral fermion, like a neutron, for example, cannot be detected by braiding with a gauge flux. Yeah, there's no gauge flux which you can detect this neutral fermion by braiding. So from that point of view, the standard model is incomplete. It's anomalous. It belongs to swampland, basically. From this qubit model point of view, at least belongs to swampland of a qubit model. And so if you believe this qubits unify everything, produce elementary particle, then that's a prediction that there must be additional discrete gauge theory, which produce a gauge flux, which allow you to detect neutron by braiding. So there's new cosmic string. And this is mathematically, this is more or less established. So in order for something to be realized by the local qubits model, all the topological stations should be able to detect each other. I think this is really analog to the completeness hypothesis. Yeah. So that's a wonderful anomaly free condition. Yeah. Since you also mentioned this UVR mixing, I just want to mention that there's a so there's a proposal that there's a symmetric tensor gauge field coming from fractals. Fractal with this UVR mixing and the symmetric tensor gauge field is very close related. And so one may have a similar thing in the swampland landscape because the fractal phase have energy gap, which can be served as a bulk topological order. And their boundary will belong to the swampland with UVR mixing. So that is one way to think about it. The boundary of a fractal phase belong to swampland with a UVR mixing. That's so that's maybe the these two topics combined. These two topics, there's something. Yeah.
Do you have examples of fractals in string theory? Maybe someone already said it, but I missed it. Is there any clear example of a fractal appearing in string theory compactification?
Yeah, I don't know. Yeah, but just
people try to construct fractal models using string theory by stacking D braids.
Nice.
So, but I do not know how far this could be pushed. So basically, there are layers of D brains, say the XY direction, XZ direction, and YZ direction. You have stacks of them, and they couple to each other, and then there's restricted mobility because of the structure. Some particles are constrained to be on one of the planes or the intersection of the plane. And there are various variants of this idea. But so as far as I know, usually string constructions are helpful because you take a problem that you don't know how to analyze in ordinary field theory, you give the brain construction, and then it's easy to analyze using the braids by drawing pictures. This is when it's effective. In these examples, as far as I can see, it is exactly the opposite.
Yeah, I just want to mention that in condensed matter, people try to construct a theory with emergent gravitons, but nowadays when you're looking back on those theories, surprisingly, those theories actually are fractal models. So, but at that time, around 2006, we don't see this connection. So it just say, oh, there's some theory with emergent symmetric tensor field. But looking back, those are actually fractals. So this would be really intriguing whether fractals have something to do with quantum gravity.
So Harvard Node, you were waving. Do you want to skip? So we'll come back to Johanna after. Go ahead.
Yeah, I was just wanting to follow up on Xiao-Gang's response to Irene. But so you were mentioning the neutron. And you're saying that the standard model was kind of incomplete because you're going to detect neutron from far away. But the neutron is unstable. So I wanted to ask if this remote detectability hypothesis for condensed matter will also, does it work for literally every lattice excitation that I can have, even if it's something that is decaying to something else? I should still be able to detect, every.
A neutron is unstable because it can decay into proton and electron. So I can think about hydrogen atoms. So it became hydrogen atoms. So hydrogen atom is no, not hydrogen atom is actually, sorry, it's neutron to not, you have neutrino, I'm sorry. So I'm thinking maybe like a helium-3, so let's say helium-3. So helium-3, let's assume it's stable. Then it's still neutral fermion.
Good. I just wanted to ask, like, this remote detectability is just about exactly stable stuff. Okay.
No, it doesn't matter if it's stable. So as long as you have so just a neutral, basically neutral composite fermion is a sign of a Swampland, basically.
But so the claim in a lattice model, like the claim is that I can detect any excitation in a lattice model from far away, even if it's.
Yeah, that's right. Okay. If it's five theory coming from a lattice qubits model, the statement will be different if your lattice model have intrinsic fermion. Then the standard model can be realized by this intrinsic fermion lattice model. But then you have to assume you have a fermion to start with. But if you assume if you prefer strong localness, so we only have a qubits, nothing else, then the emerging standard model have some constraints.
Okay, thanks.
Johanna?
Yeah, so I have a quick comment about gravitational anomalies and then another question to Nati. So the comment about gravitational anomalies that were discussed, I just wanted to mention quickly that they, of course, play an important role also in a different context of relating string theory and condensed matter, which is that they contribute to the hydrodynamic expansion as studied in applications of the ADS-CFT correspondence to such systems. And indeed, as being present in this hydro expansion, they have actually been studied by experimental condensed matter physicists by looking at the divergence of the entropy current. And so there's really effects of these gravitational anomalies which can be measured in the lab. I think somebody asked about experimental contacts. So there's quite a few experimental contacts of all these ideas. But really, I have a question to Nati. I mean, we already discussed quite a lot UV, IR mixing and fractons, but since you mentioned that you would like to see an extension of QFTs now in the context of discussion, can you give another example of an extension of QFT that would be relevant both for high energy physics and also condensed matter?
The quick answer is no. I mentioned 3 examples and I know 3 examples. And honestly, I don't know what to make of them. I'm totally baffled by it, but I don't think we can deny that they exist.
Mm-hmm. So what are these?
Somebody could dismiss all these examples as saying not being relativistic. And if you want to study only relativistic theories, maybe one can prove that this cannot happen, and then we don't need to address this question. I think that this view would be too narrow. I think that these models are trying to tell us something, but I have no idea what.
Okay, so it's a question for the future then.
Instead of the audience asking me, I'm asking the audience.
All right, thanks a lot.
Kobe?
Yeah, since the topic is new phases of matter, I would like to point out another new phase of matter that we consider recently. It is with Vadim Kaplanovsky in Mati Jarvenan. And the point is that phases of matter are not only determined by symmetries and anomalies, but also by the dynamics. So what we considered was the case of nuclear matter. Nuclear matter in large N is necessarily a crystal. In holography, like in the Sakai-Sugimoto model, nucleons are instantons of flavor symmetry. And one can get quite easily the analog of the Skir model for the properties of a baryon or a nucleon. But the question is what happens to nuclear matter? And so for that, you have to analyze lattices of nucleons, which means to solve the ADHM equation, which is very complicated. But what we did, we approximated it to a two-body interaction based on this ADHM equation. And from that, we were able to determine the phases of the system. which are in fact very rich and complex. So there are all kinds of phases depending on the different weight of the non-abelian interaction. So I recommend people to look on that point, because I think that non-abelian lattices, not necessarily in the context of nuclear matter and instantons, may be also relevant to various different condensed matter systems. And we have developed techniques to analyze these phases. Thank you.
So Steve Schenker had a comment that maybe he wants to say out loud. If not, I can read it.
Sure, I'll say that. I just wanted to, in this topic of extensions of local quantum field theory, there's this very interesting phenomenon, I guess, first pointed out by Zamolodchikov of the TT bar deformation of a conformal field theory. That seems to have various non-local aspects of a quote unquote kind of continuum theory. And it doesn't seem to have some strong UV-IR mixing. The higher energy doesn't seem to make the length of the shortest length bigger. But nonetheless, it does seem to be something that goes beyond local quantum field theory. There are pictures where it has something to do with like points becoming little rods. But it seems like it might be a nice example to try to understand. There's holographic kinds of interpretations of sort of understanding some self-contained formalism for what it is. It doesn't seem obviously gravitational either, but it does seem to be something beyond the typical kind of quantum field theory rules that we're used to. That I just wanted to raise it and wonder if people had ideas about how one should think about it.
So are there any comments on that? Okay. Andy, you had a comment on that?
Yeah, Nadi, maybe you would go even further. Would you say quantum gravity is an extension of quantum field theory?
I think the answer is yes, but perhaps this answer is not very useful. Honestly, if I had, well, speculations are free, so I'll try to make a speculation. There's one structure which includes both quantum gravity and quantum field theory. Sometimes they are the same, like in ADS. Sometimes we need to go a little bit beyond, sometimes not. But it's surprising that we already, by asking about systems that are not gravitational, we have a lot of hints that the standard framework that we have does not describe all cases. Now, I do not know whether these examples are very special, but it is a fact that all these examples that I mentioned are examples that I think to some extent also the TT bar example that Steve mentioned. These are examples that people stumbled on. They did not try, people did not say, let's look for a model which has UV-IR mixing, or let's look for a model that violates the standard paradigm that we use. Instead, people explored something and they stumbled on these examples. And that's common to all these examples. The way I view it is that it might very well be that there are many other examples like that we haven't yet stumbled on. And once we have more examples, maybe somebody will get a clear picture of what's going on here. It could also be that these examples are very esoteric and they send us in the wrong direction and they're very misleading. But that's what's exciting in research. We don't know and we'll explore it.
Nima?
Yeah, I have two questions. I think one of which was alluded to already, but I'll bring it up anyway. I guess my first question is for Xiao-Gang. In this idea, when you have gravity, for why we sort of morally think that that the entire charge lattice should be populated, we should have all charge objects and so on. It has a lot to do with black holes and horizons and the fact that you can make up any solution that you want at long distances, and where without gravity you might have a singularity that would give you a reason to throw it out. With gravity, those solutions can exist and with the singularities hidden behind horizons. So I guess my first question is there an analogous sort of moral reason that you would expect this in condensed matter systems? I don't see one, but I don't know about the subject. And relatedly, and this is also a more general question even about quantum gravity, but a very basic aspect of this, of the all charges being realized, is are consistent theories of quantum gravity forced to have fermions? And analogously, are condensed matter systems forced to have fermions? I think that's the most basic example of whether the entire set of possible charges is populated. And it certainly doesn't look like all condensed matter systems are forced to have fermions, whereas all consistent quantum theories of gravity we know of do have fermions, at least as the ones I know. So anyway, that was my question to you. And maybe I'll just quickly ask the question to Nati, although this again was alluded to. In the non-gravitational examples of UVIR mixing, I'll put the TT bar example aside because that's funny from a number of points of view. But the ones that you mentioned all involve some breaking of space-time symmetries. Either you break rotational invariance like the Fractal examples, or you turn on a magnetic field like for non-commutativity and so on. Whereas the sort of the UVIR that mixing that we think is there universally because of gravity doesn't do that. Do you think this is a technicality? You think that might be possible to find examples that are more like the gravitational sort of UVIR mixing, even without turning on backgrounds or breaking space-time symmetries?
Okay, I'd like to answer the two questions since I was asked a second, but I would like also to say something. Sure. So again, the quick answer is that I do not know. In the context of fractals, I think the main point is not that, but the point that was stressed by the condensed matter people is that at least some of these models, the theory depends not only on the topologies, these are generalizations of topological field theory, but also depend on the choice of foliation of space-time. In their case, it's foliation of space. And at least for many of the examples, once you have a foliation of space, it's true that you ruin the rotation symmetry, but this is part of the data needed to specify the theory. This is similar to your question about fermions. If you have a theory with fermions, you also need to specify choice of spin structure. Whereas in a theory without fermions, you don't need to specify. So it's not exactly the same, but it's kind of reminiscent. Regarding the relation to, regarding your point about the completeness of charges, the way I see that, and I think you and I discussed it at length more than once, in quantum gravity, we don't want any global symmetries for reasons that you articulated very well. In condensed matter physics, we think that the short distances, there isn't any symmetry. These may be lattice translation or something like that, but we don't say that the system with short distances has an F4 global symmetry, because we have no global symmetry at short distances. And there might be emergent symmetries at long distances, but they will only be approximate, very much like in the context of gravity. For the completeness charges, most of the completeness charges can be the exclusion, or the way we argue that the charges are complete are through the gauge charges are complete, or through the lack of higher form symmetries, or in a more sophisticated way, the lack of the non-invertible lines, non-invertible symmetries, like the ones that Xiao-Gang discussed this morning. And these two arguments of no higher form symmetries and no non-invertible operators exist in condensed matter physics and in gravity at short distances. So in condensed matter physics, because we start from some lattice system that has none of that, and in gravity, because this is being postulated. So the details are, of course, completely different, but the statement of no global symmetry, populating all the charges, etc., seem to be very similar.
Yeah, maybe I just want to add as in some condensed matter research, people try to produce a lattice model with an emergent spin-2 field, basically graviton. But those are very kind of limited in the sense, kind of near the flat background. So always near flat background. And at the moment, the only success is emergence of a Lipschitz gravity, with a omega k cube dispersion relation. And but I don't know. Maybe it's interesting to study the black hole in Lipschitz gravity. I don't know, but this whether there's something one can address. So actually, the lattice model with emergent Lipschitz gravity has been constructed, but whether the boundary of phase transition domain wall can be viewed as a black hole in this model, things like this have not been studied.
Okay, any other comments about Nima's questions? Shiraz, go ahead.
Hi. Of the three examples you raised, Nati, two broke Lorentz invariants, namely non-commutativity and the fractons. But the third one did not break six-dimensional Lorentz invariants, right? The little string theory preserves six-dimensional Lorentz invariants. It has other slightly weird features like a continuum of states even when the theory is put on a five-dimensional torus. But it was six-dimensional Lorentz invariant. So I was wondering whether that addresses some of these concerns. Also, related to that, you explained to us how UVIR is violated in the other two examples you studied. For instance, in non-commutativity, something going in this direction becomes big in that direction. What is the analogous phenomenon? Is there a clearly statable analogous phenomenon for the little string theory? Is it just that high energy colliding strings become big, or is it something more?
Well, unfortunately, I do not know how to answer the question. These are the best questions are questions I can't answer.
Okay, Dan, you had a question?
Yeah, I just wanted to comment about this connection between swampland conjecture type things and systems with the local tensor product Hilbert space in condensed matter physics. So I think that in holography, this connection is quite close because we think that the boundary theory is a local quantum field theory, and in particular, you can study it on a disconnected space, and the Hilbert space has to have a tensor product structure, regardless of what's going on in the bulk. I think that analogy has been pretty fruitful over the last 5 or 6 years. You can basically show that at least in ADS CFT, the completeness hypothesis is just a consequence of this fact that the Hilbert space of the dual CFT has to tensor factorize on a disconnected space. I just want to make two comments about that. One is that, the kind of intuitive thing is you can just say, well, if the space-time is emergent, then all the gauge fields in the bulk need to be emergent too, and emergent gauge fields always obey the completeness hypothesis. So that's one way of kind of understanding the connection to what Xiao-Gang was saying. More generally, I think this factorization of the Hilbert space on disconnected spaces with disconnected boundary can be used to argue that there should be no topological surface operators of any kind in the bulk. And I think all of these conjectures in some level are just saying there shouldn't be any topological surface operators in quantum gravity, which I think certainly from this factorization point of view is obvious, because if you have a topological operator, you can move it right up to one boundary, or you can move it right up to another boundary. And it's the same operator either way, but in a tensor product Hilbert space, that's not possible. So then finally, just a question to Nati. I know you don't like Lagrangians, Nati, and I know why you don't like them, but if you want to give someone a quantum field theory, it sure is a pretty efficient way to give them a quantum field theory. Can you imagine some other way that's as efficient? I mean, most of the other ways are just like, here's a list of all the correlation functions, which is not very efficient.
So if I can try and answer, I don't think it's fair to say that I don't like Lagrangians. I love Lagrangians. But as I said in the slides, these are different presentations, and every one of them has its advantages and disadvantages, but none of them is universally valid. So I do not even know how to write a Lagrangian, say, for the 2-0 theory. Yeah. So this is not going to work there. Also, many of the integrable systems are solved without ever mentioning an underlying Lagrangian. The connection to a Lagrangian is often described only after the fact. Once you look at the solution, you say, aha, this solution is a solution to a particular Lagrangian system. Now, I'm making blanket statements, and there are many counterexamples and so forth, because it's a very complicated setup. All I have in mind is that Lagrangians is not a magic bullet that solves all the problems.
But it would be a pity if we had to make do with the list of all the correlation functions, right? I mean,
well, it would be a pity if this is the final answer, but at least it's correct.
Yeah.
And for what it's worth, it's not correct in the little string theory because you don't have the local operators. This is just to show that there's still a lot to understand.
Harvard Node, did you have another question? Go ahead.
Yeah, so I have a question for Xiao-Gang Wen. So you've been describing like this very nice analogy between the more topological aspects of the gravitational swampland program and the one in condensed matter. But in the swampland, you also have like more dynamical statements where you constrain kinematic, like precisely constrain kinematic properties of states, like the Wigger-Ratti conjecture and stuff like that. And so I wanted to ask if there's something like that in the lattice swampland program, or if this would be a point where we can really see a difference between the two.
Yeah, actually, I don't quite understand your question. Let me see.
I'm just saying that, for instance, in the swampland, we say that there has to be a particle whose mass is lower than its charge in Planck units, something like that.
Oh.
So can we say something like that from the lattice point of view?
In some sense, yes, and but in different aspect. Actually, there are certain, for example, certain field theory in swampland, because it's a boundary of a certain special kind of topology order in one higher dimension, then this field theory has to be gapless. So that's what is we just hear that there's a talk, Soha's talk, yeah. So it's so this kind of thing appears, and also if there are some field with a low mass, and then there may be separation of energy scale. When you have a separation energy scale, and there'll be interesting. That's be very interesting question. So let me say that another way. Suppose you have a lattice theory, and you have a separation energy scale. The low energy effective field theory for the low energy particle alone may be anomalous. There's this well-known phenomenon, and so therefore, if you ignore some high energy excitation, then the original lattice theory became anomalous theory and belonged to swampland. And so actually this is why in condensed matter, the study of swampland is so interesting, because when we have energy scale separation, when we study low energy physics, then the phase diagram dynamics coming from those low energy particles actually belong to swampland physics. And it's better to study them as a boundary for topology in one higher dimension once you ignore the heavy part of the theory. So this may be an effective way to study low energy dynamics. And I think in this, today we hear this for this non-abelian gauge theory. And if you only consider a fluctuation of the gauge field strength, but no charge is allowed. And assuming charge very, very high energy, then this theory may be anomalous in some sense, and then or may have some different symmetry. So that may provide some dynamics. Yeah.
So there are no situations where we can say something like there has to be like certain kind of charge excitations whose mass is much below the lattice spacing or something like that. So of course, naturally things to happen at the lattice scale. But
yeah. That's what I mean by energy scale separation. When I say energy scale separation, let's consider some particles whose energy much less than a lattice scale. And those particles may give you effective field theory, which may be anomalous, maybe belong to swampland. And under this assumption, you can treat this system as an anomalous theory and treat them as a boundary for some topology order. But once those light particles became heavy, this approximation, this point of view, no longer valid. So then you should not think that way.
Okay, thanks.
Irene, you have to say something?
Yeah, maybe another way to ask this is if you can somehow quantify how approximate the symmetry can be. Like if something goes wrong, if you try to suppress a lot the breaking effects or to have the very small gauge couplings. And I was wondering if maybe you can see it because there is some anomaly, but the gauge field is massive. So as long as you are below some energy scale, seems fine, but then you can get sensitive, I don't know, to when that phase, and then you get sensitive again to some sort of anomaly.
Yeah, it's related to the questions. Let's consider Z2 gauge theory. Let's consider Z2 gauge theory. And the Z2 gauge charge would have a Z2 symmetry, emergent Z2 symmetry. And but once we ignore the Z2 gauge flux, then we really have a Z2 global symmetry. And but once the Z2 gauge charge, Z2 gauge flux have same energy scale, suddenly we don't have any symmetry. This just became Z2 gauge theory without any symmetry. So I think that is that was the thing I refer to. But however, those emergent Z2 symmetry in some sense exact Z2 symmetry, I think. And let me see. Can I say that? Yeah, because there's a Z2 charge have this Z2 fusion rule, so which is exact, not approximate. Even that's what I'm thinking. Yeah.
So let's go to Greg Moore. Greg, so you're mute. Okay.
Yes. I had a small, silly question for Nati and then a comment on Nati's first slide. The silly question: if you had a periodic renormalization group flow, would you say that's UVIR mixture?
Maybe, yeah.
Okay. I mean, I have been in talks where people have claimed to make perturbations a little bit like the TD bar, but not exactly where they claimed periodic renormalization group flow. The comment. So you had a list of approaches to quantum field theory on your first slide, and maybe I missed it, but I think you left one off. If you ask a mathematician what is a field theory, then the mathematical community actually has an answer. You might not like the answer, but they have an answer. And their answer is that you have a geometric category of some kind. I could be more precise about what is a geometric category. And it's an N category. It's a monoidal N category. And you have a target category. I see people are smiling, but I think you should take it seriously. And you have a target category, which is also a monoidal N category, and a field theory is a functor from one to the other. And that captures a lot. That captures a lot of the stuff about defects, generalized symmetries, and so on. The Bordism category need not just be a simple Bordism category, which is what you would use in topological field theory. You can have all sorts of extra structure. You can have a Riemannian metric, a spin structure, all sorts of tangential structures. And so that also comes, so that's what mathematicians mean by a field theory. And they apply, that's a very flexible notion. They apply field theory, the ideas of field theory in very remarkable ways. I mean, just look at conferences on the geometric Langlands correspondence, for example. And as people were asking about what are generalizations of quantum field theory? Well, there are a lot of monoidal N categories out there. That gives you a lot of generalizations of field theory.
Okay, we're running out of time, so let's just, Igor, you have just a comment based on what Greg asked?
Yeah, actually, since Greg brought up RG limit cycles, I just wanted to mention if one is willing to accept that quantum field theory, say with ON invariance, continue to non-integer n and say in 3 minus epsilon dimensions, if one accepts this as an okay quantum field theory, then recently Christian Jepsen, Fedor Popov, and I actually wrote a paper on a completely perturbative periodic RG flow. A disclaimer is that it's not a unitary theory. You always have some operators with negatives, homological type metrics, so it violates the F theorem, but nevertheless, it's something that just follows from beta functions computed at 2-loop order. And there are various other examples that Christian Jepsen and Fedor Popov are pursuing now. So it's possible completely perturbatively from beta functions.
Okay, let's just finish with the last question or comment of Jake McNamara. Go ahead.
Hi, yeah, my question's for Xiao-Gang. One swamp lane conjecture I don't see analogy in a local qubit model is the absence of free parameters. So I was wondering if you have any comments on that, because in quantum gravity, we expect that every free parameter in the Lagrangian is the VEV of a dynamical field, but I would think that a local Hamiltonian has tons of free parameters, and I don't see them being realized necessarily as the VEV of some dynamical excitation.
Yeah, indeed. This is maybe this is a big difference. That is, the Qubits model have a lot of free parameters. It's very, very ugly. So only effective field theory maybe is nice and beautiful. And just a lot of those free parameters became irrelevant at the effective field theory level. But indeed, they have a lot of models. But on the other hand, I feel this free parameter issue probably is related to the following. You know, I want to really say that Qubits model really quantum gravity is because although space-time metrics not specified, it's a lattice model. But however, some kind of a space-time framework is kind of there. There's a sense of a closeness, a distance, a sense of neighborhood is somehow predefined. And so this feature, how this feature was, that would be different from gravity. But what I really want to stress is a really a question. You know, I'm surprised that the condition on effective field theory, which coming from quantum gravity, and the condition on effective field, which come from Qubits model, is so close. So it would be really interesting to see whether there's some difference condition, that some conditions are really different. You know, you say this effective field can only come from quantum gravity, cannot come from local Qubits model. That would be really, really interesting. So then we can understand this issue better. Yeah.
Okay, Peter has a final question, but okay, go ahead. We're running out of time, but maybe you can just pose it and people can try to answer it in Slack. Go ahead, Pedro.
Okay, so let me just ask a very naive question. How does this very mathematical corner of condensed matter, I mean, from an outsider, beautiful structures, but full of categories and so on, can you give us a brief description of how does that connect to experiments and to the more traditional condensed matter where we see materials and bands and stuff? Are there parts of it that are totally disconnected and parts of this that are more connected, or is it still, or everything is connected, or everything is disconnected? Could you just give us some flavor of how that works?
Yeah, and I think this question is asked more in condensed matter community. It is a right direction for condensed matter. And but on the other hand, it's really that I think in the quantum material, we indeed facing this so-called highly entangled quantum system. And so there's an issue about how to characterize this highly entangled quantum system. How to characterize many-body entanglement. And we know that when you have a symmetry, we need a group theory to characterize symmetry. But it looks like to characterize quantum entanglement, those anions, non-abelian statistics, or more generally, this category theory appear to be the right language. So that's why those kind of category theories somehow enter condensed matter, because it looks like it happened to be the right language to describe a highly entangled system. And you know, it's for the experiments, usually experiments only realize some very special states, like Ising category. And but to study Ising category, one don't need to study category. One can using Majorana zero mode. So most people do not use category language to study Ising category, but using Majorana zero mode language. And so that's you can obtain condensed matter experimental available results. And but however, I think the Ising category probably is maybe most complicated experimental relevant category we encounter in condensed matter in real material. Although it's still not confirmed yet, but there is very likelihood that there are certain quantum Hall states are described by Ising category. And this Fibonacci category, there are some expectation, some proposal, but it's far from confirmed experimentally.
Okay, so let's close the session, but of course people can continue to communicate via Slack. So thanks very much, Nati and Xiao-Gang, and we'll be back.
Thank you. Sorry again, Nati and Xiao-Gang.
Yeah. Thank you.
Thank you.